Hi, everybody. We're kind of at the end of chapter 20 now, chemistry and nitriles. Fortunately, this is not that crazy of a section, maybe compared to some of the other ones. And we already know some of the chemistry of nitriles, even from organic 1, where we learned how to make them by like SN2 reaction, right? So you could take something with a leaving group on it, like a bromide or something, and then throw in cyanide, CN minus, and that would kick off the leaving group, and you'd be left with a nitrile, right? So you learned about at least how to make them as early as organic 1, and now we're just going to do some more of the review of the preparation of them and some of the reactions of them, kind of like we did all these other functional groups this chapter, like acid chlorides, esters, anhydrides, amides, etc., etc. All right. So yeah, this is old organic 1 stuff. Like you could use usually a primary or maybe secondary bromide or chloride or leaving group, and react with like Na plus Cn minus, which you could also just say is NaCN or something, KCN, NaCN. Which is Na plus Cn minus, and then it's just a SN2 reaction where the carbon attacks the carbon with the leaving group. Leaving group goes away. It's all concerted SN2 reaction, right? Maybe use a SN2 solvent like DMF. This is all from last time. And then there's also this class of nitriles that kind of look like a Grignard addition product almost, and you can react ketones and aldehydes with HCN and then NaCN, and the mechanism is incredibly easy. Oxygen grabs the proton first to make a RSCC, which you could draw. I'm not doing this because we did it before, and then show the carbocation, and then Cn minus just attacks it. Another example, cyclohexanone, the 6-member ring. Alcohol and nitrile. And these again are called cyanohydrins. Cyanohydrin is when you have an OH and a CN. Okay, so those are a couple ways to make nitriles that you are familiar with. Okay, so again we're on number 9, which is nitriles, chemistry and nitriles. And we did A, which was making them. By the SN2 and cyanohydrin method, making or synthesis of. Now we're on to B, which is some of the reactions of nitriles. One of them is hydrolysis to carboxylic acid. You actually know this. This is all, I think we learned it in chapter 19 originally. Example is nice nitrile, and we can react it with H3O plus and make a carboxylic acid and ammonia, NH3. Okay, and yeah, the mechanism, again, I'm not going to do it for you again because you know it already, is you protonate the nitrile. And then it's going to be kind of like this long sequence of like, make an RSCC, 4 carbons, right? 1, 2, 3, 4, 1, 2, 3, 4, yeah. And make an RSCC plus charge on nitrogen, kick the electrons up to nitrogen. I'll start it, you guys can finish it. Now you had a triple bond, now you have a double bond. And where's the charge now? Where is the charge now? Charge has got to be somewhere. It's not like the charge went away. Charge is on carbon. And then water would attack. I'll probably stop pretty soon because you can do this, right? water attacks, then you have a plus charge oxygen, and you proton transfer to the nitrogen, and basically at that point you can attack a second water, and then you have your two oxygens then, and then just kind of keep going. I think this is even a quiz question because it's a fun mechanism. Look back a quiz or two ago, and you should be able to find this, because I always make this as a quiz question because it's a good mechanism question in terms of just following the charges, doing your proton transfers, your RSCCs, etc. So you keep going with this. You can try it yourself, and if you get stuck, go look at the earlier quiz, right? And it eventually winds up at the I think probably the last step, like all of these last steps with acid, is you probably have a protonated carboxylic acid. And what's the last step of that? Minus H plus, right? Minus H plus. Okay, so yeah, anyway, hydrolysis of nitriles leads to carboxylic acids, right? You can also do this with base. We can do it with acid, or we can do it with base. The base mechanism I don't think is as elegant, so I usually don't care about it as much, at least for this course. But you could probably try it yourself. If you want. You're not going to see it on my quizzes, at least. Hydroxide attacks, kick electrons onto nitrogen, and then you kind of do the same sort of protonation, and you have water around of the nitrogen, etc., and then eventually nitrogen falls off as a leaving group. You're welcome to try this, but I think if you're going to practice anything, we'll probably do the acid catalyzed reaction. Okay, so that was B. That was hydrolysis, right? All right, so hydrolysis to carboxylic acids is one thing you can do with a nitrile. All right. The next kind of cool reaction is C, which is reaction with Grignards. Because remember, that's been a kind of fun thing in this chapter, is reacting different functional groups with Grignards to see what you get, right? And like if you react a Grignard with an ester, what do you get if you react a Grignard with an ester? You get a tertiary alcohol, right? So also if you react a Grignard with an acid chloride, you also get a tertiary alcohol. And what else? We also learned like acid chlorides react with something else to give you a ketone, right? Remember that? Acid chlorides? Acid chloride. I'll just draw that up here. Acid chloride. There is something special that you can react with to get a ketone, right? From an acid chloride. And that was a cuprate. So you could use like dipropyl cuprate, copper, lithium. So it's two propyl groups, right? Two propyl groups. It's propyl, and then, but there's two of them, and copper, lithium, and of course you need a step 2, which is water. And that is a way to make a ketone from an acid chloride, is using cuprates, right? Okay. Anyway, so nitriles react with Grignards to make ketones also. In kind of a similar way to how cuprate reacts with an acid chloride to make a ketone, nitriles react with Grignards to make ketones also. The mechanism is a little different, but let's do that now. Okay, so how does a Grignard react with a nitrile to make a ketone? And also, I'll say right now, the acid chloride thing is really unique to acid chlorides. Sorry, cuprates. Cuprates reacting with acid chlorides, right? Cuprates kind of uniquely react with acid chlorides. They also do the 1,4 addition to enones that we talked about, but none of the other carboxylic acid derivatives react with acid chlorides. It's just, none of the yeah, none of the carboxylic acid derivatives react with cuprates except acid chlorides, and those give ketones, all right? But a nitrile reacts to the Grignard to also make a ketone. So it's another way to make a ketone. Okay, so let's just show how it works. Here's a silly nitrile, and we're going to react with the Grignard, like phenyl Grignard. This is a nice easy one. And some kind of water or as acid. Second step, alright? H3O+. And net result is you get a ketone out. So we have our 4 carbons, and then we have a ketone, and then in this case phenyl. Okay, so how does this all work? Well, what do you think the first step is? What do Grignards do to things? They are nucleophiles, and that's an electrophile. So this is delta minus, delta plus, right? So the carbon is kind of electrophilic, that's nucleophilic. So the way I like to do is I circle the bond and then I go attack. Kick electrons up onto nitrogen. Alright? And what does that give us? So now we have nitrogen, we have our phenyl group that we just added. We had 1 lone pair. Now we have 2 lone pairs because we kicked electrons onto nitrogen. So now we have 2 lone pairs on nitrogen. And what's the charge on nitrogen? Negative charge. Okay, good. If you had a counter ion, it would probably be MgBr+, but that's not critical to draw. MgBr+. Okay, anyway, so something negative, something positive. And then and then it basically stops. This stops here. It's not like Grignard attacks again, like to the carbon. Okay. The funny thing though is, remember that lithium aluminum hydride, which does react with nitriles, kind of reacts the same way. Lithium aluminum hydride attacks once, but then it also will attack again, and your net result will be an amine. We'll see that in a second. But a Grignard only attacks once. Grignard attacks once, you get this funny carbon double bond nitrogen negative thing. And then how do we go from carbon double bond nitrogen to carbon double bond oxygen? Maybe it involves the water, the acid water, right? Okay, so what I do is now I just assume H3O+, and we just do assume twice. By that I mean we're going to protonate nitrogen, and then we're going to do it again. So we protonate once, we protonate twice. So I'm just going to say, okay, well, we protonated twice. What do we get once we protonated twice? Got a plus charge. Now on nitrogen. I wanted to sneak in the mechanism going upward, but it looks like I have to go down and wrap around. It's not that hard, but it's a couple steps. Okay, this is an RSCC, right? So it's like we have a double bond nitrogen with a plus charge. You can push the electrons up on the nitrogen now. Now where's the charge? When you're doing this in your notes, if you do this right, you just kind of make this go a little bit deeper down and around, and then you won't have to do what I'm doing. You can just kind of go down all the way around and back up. I just ran out of space because I screwed up. But anyway, where's the charge now? So I'm plus charge on the carbon. Of course, this is an RSCC. It's a resonance stabilized carbocation. Okay, so now I'm just going to have water attack the carbocation. I'm going to sneak it around there. Okay, water attacks the carbocation. And now water's attached to that carbon. maybe I'll just do it up here, OH2 plus nitrogen, HH. What do we need to do now? We got to get rid of the nitrogen to make a ketone, right? Our final product's a ketone, right? So what are we going to do? Probably we need that oxygen, we don't need the nitrogen, so we're going to proton transfer from the oxygen to the nitrogen, right? PT OH NH3 plus. Okay, now oxygen kicks off nitrogen and you're basically done. And now we have a protonated ketone, right? All we got to do is go all the way up top, all the way up top, all the way up top, all the way up top with a minus H plus. Minus H plus, loss of the proton on the oxygen, goes all the way up, and then we get the ketone, right? So yeah, probably if I would recommend if you do this in your notes, rather than do what I did, it was kind of like this silly little loop, you should go more like, no, and then you're up there, and you don't have to do this weird, long minus H plus thing. Okay, so that's how a nitrile reacts with a Grignard to make a ketone. Okay, is there a name for this thing? This thing, there's a name for that. It's, you know, what was this called? If you just have a C double bond N, it's called what? It has a name. C double bond Ns are called imines, right? But if you have a positively charged imine, it's called an iminium. Iminium. So, okay. So that when the Grignard attacks, and then you protonate this intermediate, you get an iminium, which is an RSCC, and then that gives rise to the electrophilic carbon. Water attacks, water's attached now. You can proton transfer from oxygen to nitrogen to make a good leaving group. Okay, now it's NH3 plus, oxygen kicks off the NH3, get a protonated ketone, and then you minus H plus, and you're all the way done. Okay, it's not that crazy of a mechanism. All right, I hope you agree. That's not that crazy of a mechanism. Okay, so we have this cool reaction that takes nitriles and makes ketones. Let's just do an example now. Maybe I'll do convert this alkyl halide into a nitrile. How do I do that? What's a good way to make nitriles from alkyl halides? Maybe NaCN, NiTMF. Good old organic 1 chemistry, right? Just SN2. Carbon attacks carbon, kicks off the Br, and you get the nitrile. And then, like, if I want to convert this to an arbitrary ketone, like an isopropyl ketone, what would I react with? Well, what's changing in the molecule? Obviously, the nitrogen's going away, and you're getting left with oxygen. But the nucleophilic thing we're attacking with is what? How many carbons is that? 1, 2, 3. 1, 2, 3. It's 3 carbons with the branch on the middle, so it's isopropyl Grignard. Isopropyl Grignard, and then acid water. It's 3 carbons MgBr on the middle, right? Isopropyl Grignard. All right, cool. So that's a good example of how we can go from well, in this case, alkyl halide to a nitrile, add a Grignard, and make a ketone. Okay, I think we're on the last little bit of nitriles. Again, this was not that crazy of a section, I hope you agree. Now we're on D, which is reduction. And by reduction, it's usually going to mean H minus reagents. H dot dot minus reagents. So we're going to reduce the triple bond to nitrogen to either a single bond to nitrogen or a double bond to nitrogen. Right? There's basically going to be two different situations, and this is mirroring the other functional groups we learned about this chapter. Right? We got H dot dot minus two equivalents, and this is going to make an amine. H dot dot minus two equivalents will be an amine. We'll show you that in a second. But it's you already know this. So you learned this before. This is not the first time you've seen this. And what's the typical H dot dot minus two equivalents reagent? Super strong reducing agent, lithium aluminum hydride. Okay, just like always, use a super strong reducing agent, and that will deliver to H dot dot minuses and make an amine. Okay, but what is new, and not too crazy, is that if we do H dot dot minus one equivalent, what's it going to make? This one might be a little less obvious, but it makes an aldehyde. Okay, and then what is the H dot dot minus reagent for one equivalence that we've learned and used a couple times in this chapter? Like for esters and amides, because you have learned an H dot dot minus reagent that delivers one equivalent of hydride, and it begins with D and it's 5 letters. 5 letters and begins with D. What is it? It's dibol. Dibol or dibol H, whatever. It's all the same thing. Okay, or dibol, diisobutyl aluminum hydride. Okay, so let's just show these two with simple examples, and then we're done with the chapter. So for the H dot dot minus two equivalents, hydride two equivalents, let's just show a random nitrile. Let's make it chiral for no particular reason. Make our nitrile nice and linear. Don't make a bent nitrile. Okay, and then we know this reaction because you learned it before. We're going to react with lithium, aluminum, hydride, two equivalents or excess, and H3O plus. Okay, and this is a pretty simple mechanism. We'll review it. But essentially, what you're doing is you're adding H once, you're adding H twice, and you get an amine. So of course there's two H's there. I'm not showing them, but let's just show them. Why not? So we add these two H's. Those are delivered from lithium aluminum hydride, those two guys. Okay. Alright, so how does this work? This is old news. You've learned this before. I forgot where you learned it. Maybe it's chapter, I don't know, chapter something. you have learned this though when you learned about nitriles a little bit earlier in the course. Okay, so lithium aluminum hydride is basically H dot dot minus. So we circle on pair, attack. Okay, that's easy. It's following what you know about nucleophilic addition of hydride. Then we have an H. And dot 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 minus. Right? Okay, and then it just does it again. Does it again immediately. This is what I was saying that's kind of different about reduction versus Grignard attack, right? Because with Grignard attack, it kind of does the same thing where it attacks once and then you get it here, but then it stops. But with the reduction, with H minus 2 equivalents or lithium aluminum hydride, it reacts once, then it does react again, and so second time. And then what do we get? this kind of crazy looking thing. The structure of it is kind of weird. Not only do you have 2 lone pairs, you have 3 lone pairs on nitrogen, right? What's the charge on nitrogen now? It's 2 minus. You have 2 negative charges on nitrogen, which is very unusual. You don't really see nitrogen with 2 negative charges. Okay? But anyway, then you just carefully drip in some H3O plus, and then both of the nitrogen, you get 2 protons incorporated onto nitrogen, flip it around, and you get this final product. Okay, so this is actually old stuff. You have learned this before. You may have forgotten it, but you can do a double reduction of a nitrile to an amine. All right. And what was the other one? I said, oh, H minus 1 equivalent makes aldehydes. How does an aldehyde form from a nitrile? Let's do that real quick. So this will make an aldehyde. I'll do the same silly nitrile. Okay, now we're using dibol or dibol H. Dibol or dibol H or diba, all the same thing. Acid, water, and so essentially you get an aldehyde. Okay, it's a H dot minus 1 equivalent reagent, meaning only 1 H gets delivered. Okay, so this, just like with lithium aluminum hydride, it's still a hydride source. It's just a little different, right? I've drawn this 1,000 times for you now. Dibol, it's diisobutyl aluminum hydride, which is just ALH. Isobutyl, isobutyl, but we're just abbreviating it as another H minus. And this is an H minus where it only reacts once because you get a temporarily stabilized intermediate. This is exactly why. Esters stop also. I think amides also stop. You get this intermediate, you have an N minus, ALX2, I always say ALX2 plus, so it's some kind of salt between a negative thing and a positive thing, and this is temporarily stabilized. And by temporarily stabilized, I mean non-reactive. It kind of is shielded for additional reactivity from H minus. This thing is kind of stabilized until we add acid. We add acid, and that destroys any remaining hydride because this is, H minus loves H plus, so this will create H2. H2 is created from H minus reacting with H plus. And furthermore, this thing gets kind of changed around a bit, and now you have an iminium. Just like we had an iminium in the Grignard reaction, right? Okay, and then water reacts with this. I'll just say C above. Go look at the Grignard thing, right? It's the Grignard reaction thing that we just showed. We also got to an iminium, and then we showed how water would react with it. So you can draw the RSCC of this, have water attack, and then proton transfer to nitrogen, kick off ammonia, and then you get your aldehyde. That is how dibol does a single step reduction from a nitrile to an aldehyde, kind of through the iminium intermediate. Iminium. And it shares a little bit of mechanism with that Grignard reaction mechanism, which you can go review. So when I see C above, I mean go look at the Grignard mechanism. It was that big long mechanism that we looped around, right? Okay, cool. I think that's the end of chapter 20. We made it. Now we go to the next chapter, chapter 21. Alright, we're entering chapter 21. We only have a couple more chapters to go. Chapter 21 deals with the amine functional group, and it's another functional group chapter. We learn how to make them and what some of the reactions are. Nothing too crazy. There's going to be a couple new reactions, and but it's just another functional group, right? It was an amine. Amines are these nitrogen things that are connected to one or two or three carbon atoms, right? There's a lot of pharmacologically active amines. A couple are shown here: nicotine, cocaine, which has this kind of abridged ring system; quinine, which is a totally different class of molecules that's used. Well, actually, it's an anti-malarial drug, and it's also found in like gin and tonic and tonic water. So it's actually used as a flavoring in beverages, but it has a couple nitrogens and including this heterocyclic quinoline thing at the bottom, and then you have the tertiary amine up top. Antidepressants pretty much all have nitrogens in them. Fluoxetine, which is Prozac, it's a selective serotonin reuptake inhibitor, has a couple benzenes, and it has a secondary amine right here. Most of the, I think all of the opioid analgesics have nitrogen in them. A lot of drugs just have nitrogen in them that are used to bind to receptors, I guess, in your body. And so morphine, codeine, and diacetylmorphine, which is also known as heroin, are based on the same general chemical structure, and they also have this tertiary amine type thing here. A lot of the differentiation of these molecules has to do with the not with the nitrogen, but with these R groups on the benzene and the cyclohexene down here. Imipramine is a tricyclic antidepressant. It's another class of antidepressant drugs. There's a whole bunch of these tricyclic antidepressants. Why are they called tricyclic? Because you have three rings, right? So there's a lot of variation of the nitrogen and also the amine, the top nitrogen and the bottom nitrogen that change the activity of these antidepressant drugs. Amines are also found in as neurotransmitters. So there's a lot of neurotransmitters that have amines. I think maybe all of them. Serotonin, epinephrine, which is also called adrenaline, norepinephrine or noradrenaline. So these are all like some kind of benzene or heterocycle, like an indole, and then or a benzene, and then you have a couple carbons and a nitrogen. I think pretty universally it's going to be two carbons off the aromatic ring. And acetylcholine is a weird amine with three methyl groups on it. It's called a quaternary ammonium. Glutamic acid's interesting because it's actually just an amino acid, but it's also used as a neurotransmitter in our brains. And also aminobutyric acid, or GABA, is another slightly different amino acid. Okay, there's about 10 neurotransmitters in the mammalian nervous system. Okay, now just as a general guideline for how neurotransmitters work, specifically things like serotonin, the neurotransmitters are packed into these vesicles in an axon, and they get released into a synaptic cleft, which is just a little space between the axon and the dendrite, and then they can get repackaged into the vesicles through this reuptake process. So there's just a little mini cartoon slide for how neurotransmitters actually work, and there's a ton more about these things that you might learn in a neuroscience course or neurobiology or something like that. Okay, and so amines have a sort of a categorization, sort of the way that alcohols have categorization, and we can classify them as primary or secondary or tertiary, or this thing called a quaternary ammonium. Okay, and it has to do with the number of things on nitrogen. So a primary amine has one thing, secondary amine has two things, a tertiary amine has three things, and the quaternary ammonium has four things, and since it has four things, it has a positive charge. Okay, so you can calculate the formal charge and see why it's positive. Now this is a little different than the way we categorize alcohols. We also categorize alcohols as primary, secondary, or like tertiary, but it's not due to the number of things on the oxygen, because you only got one thing on the oxygen. For alcohols, it's the number of things on the connecting carbon, right? So a primary alcohol has one connecting thing. Secondary alcohol has two connecting things on the neighboring carbon, and tertiary alcohol has three things on it. Okay, this is a little different, but we still use the same kind of categorization. The naming is often pretty simple. We just kind of add the word amine at the end, and then there's a couple tweaks we have to consider. Diethylamine, what do you think it is? Well, it's an amine with two ethyl groups, right? Cyclohexanone. Cyclohexane and an amine, right? So is it primary, secondary, or tertiary? Well, probably going to be a primary if it's just got one thing on the nitrogen, right? Okay, 1,4-butane diamine. That's pretty straightforward. 4 carbons, and then we have nitrogens on number 1 and 4. This also has a lovely name called putrescine, and that kind of points out the sort of stinky nature of almost all the amines. They all kind of stink in a very consistent manner. So putrescine doesn't stink much more than the other ones. It's just, for whatever reason, in history, this molecule got named putrescine early on. 1,5-pentane diamine is 5 carbons, and it's got amines on 1 and 5. So I mean, it's a pretty easy one to draw. 1, 2, 3, 4, 5. Yeah. It also has a lovely name called cadaverine because it smells very nice. It's actually found in like decaying flesh and things like that, and it just has the kind of standard sort of nasty amine smell that you kind of get familiar with when you work with amines in the lab. Substituted amines. So you can imagine amines get a little more complicated. 2-bromo-3-methylpentane-amine. 2-bromo-3-methylpentane-amine. Well, I always look at the end of the name first and then go backwards. So pentane-amine would refer to an amine with a 5-carbon chain. Amine on number 1, and we got a bromine on 2 and a methyl on 3. Okay, so that's pretty straightforward. NN-dimethylpropane amine or NN-dimethylpropylamine, they're the same thing. So it's always look at the end, and you're like propylamine, 3 carbons, nitrogen, and then this NN-dimethyl, that refers to like other stuff that's on the nitrogen, like a pair of methyl groups. So it's a tertiary amine. That's the structure for this amine. Okay, this one gets a little scary, and remember, even though stereochemistry is important in organic chemistry, I'm not really emphasizing it much in organic 2, just because some people's stereochemistry is a little weak still. But anyway, R-cis-3-pentene-2-amine. Think about the kind of right side of the name first. 3-pentene-2-amine is probably going to be an alkene on 3 and an amine on 2, right? Okay, and then the cis is describing the stereochemistry of the alkene, and the R is referring to the stereochemistry of a chiral center, right? So looking at the structure, it would be like this, and of course you see the 5 carbons, pentene, 2-amine. It's cis, it's a cis alkene, and then the R refers to the stereochemistry on carbon 2, and You know, like when I teach Organic 1, we emphasize this thumb rule thing where like prioritize like the nitrogen is A, and then the alkene is B, the methyl is C, and then the H in the back is D, and then right hand and it's like R. I don't know. Anyway, that's stereochemistry stuff, and you'll need to know that for like things like MCATs and GREs, but we're not going to emphasize it much in chem335. N-ethyl 2-phenethylamine. So again, the N-ethyl would mean you have an ethyl on the nitrogen. 2-phenethylamine is basically benzene and 2 carbons. Benzene and 2 carbons and nitrogen, and the nitrogen's on carbon number 2. Actually, I think that it's the number. I think the numbering, though, as I drew it, is wrong. I think it actually. Yeah, I think it's. I think the numbering is actually 1 and 2, but regardless, this is the structure of it, and this is just another example of an amine. Okay, and then we have aromatic amines. So it's a benzene and a amine. They're also called anilines. Anilines, and the parent compound is benzene NH2. That's pretty easy. This is different than the amino acid alanine. Alanine versus aniline. Sometimes people get confused about that when you're learning it. The amino acid structure is just, you know, amine on the alpha carbon of with the carboxylic acid, and then you have a side chain, which is a CH3, and that's called alanine. Okay, just another derivative of aniline, which is 3-bromo-4-methoxybenzene amine. It's pretty straightforward. You could also call this 3-bromo-4-methoxyaniline, right? Because benzene amine means aniline. 3-bromo-4-methoxy. So it's just a benzene with a bromine on 3 and a methoxy on 4. Another one, para-amino-benzoic acid. Para-amino-benzoic acid is benzoic acid with an amine para. It's pretty straightforward. This happens to absorb ultraviolet light very intensely, and when molecules absorb ultraviolet light, what do you think they might be used for in like skincare? They could be used as like a sunscreen, and PABA you find in a lot of chemical sunscreens, and there's other sunscreens that all kind of absorb UV light through some other different method. Anyway, so yeah, this person appears to not have very much sunscreen on them, and they have the sun smiley face burnt into them. Okay, the structure of amines is kind of like the structure of alkanes, for example. Alkanes that are sp3 hybridized have bond angles of about 109.5. That's because you have 4 things around carbon, and they're equally spaced. Nitrogen also has 4 things around it, so it's roughly, you know, almost tetrahedral. It's pseudo-tetrahedral, 108 degrees roughly. And being semi-tetrahedral, nitrogen could be considered chiral, and you might be able to, like if A, B, and C were different things, you would think that nitrogen would be a chiral center, right? You would kind of think that, right? Well, it's kind of true. There's some cases where nitrogen is actually chiral, and nitrogen can be a chiral center. In most cases, these things can interconvert, and they don't really preserve chirality, but we'll see a couple exceptions to that in a second. So normally amines and these kind of chiral amine structures will equilibrate at room temperature. So that means they can't really preserve chirality like the way carbon can, like a carbon chiral center, how it, you know, it might be R2-bromobutane or something, right? So amine isomers cannot be isolated as single enantiomers. And for that reason, most amines are not considered chiral molecules. So there's this rapid equilibration between these supposed enantiomeric forms. However, again, there's going to be an exception to this in a second. All right? And this kind of shows it also. It's like a pretty small energy barrier between the two enantiomeric forms. So you couldn't really isolate an amine and say, it's a single enantiomer, because it so readily interconverts. Maybe at extremely low temperature you might be able to do that, but for the most part we don't consider a simple amine with 3 things on it to be chiral. Okay. And so then if you look at a molecule like cocaine, which has a tertiary amine in this sort of alkaloid structure, it has a methyl group and there's a lone pair of electrons, right? You might consider, that's a nitrogen with, looks like a chiral center, right? It's like the nitrogen has 4 things on it. It's got a lone pair, it's got the methyl, it's got this bottom half of the ring and the top half of the ring. You might say, chiral center, right? It's got other chirality also, but the thing is about this N-methyl group is it can interconvert back and forth very readily, so we don't consider the nitrogen like a chiral center. It does have 4 other chiral centers that are present. In other cases, nitrogen can be locked in multiple rings and cannot invert, and in those cases nitrogen can act as a chiral center. So there are cases where nitrogen can act as a chiral center. Yohimbine is one of these molecules where the nitrogen is a tertiary amine, and it can kind of preserve chirality in the ring. And of course, we have other chiral centers, but these kind of nitrogen atoms are considered chiral nitrogen. It's a little different than the N-methyl group in something like cocaine. This is a really cool molecule also. It's called Troger's base. There's no carbon chiral centers, right? No carbon chiral centers, like the way yohimbine or cocaine has carbon chiral centers, right? But it does have a pair of nitrogens. It's got this CH2 thing, which could be pointing towards us or pointing away, and this can actually be isolated as enantiomers, which are the single non-superimposable mirror images, right? Enantiomer. So it was actually made the first time in 1887 as a racemic mixture, so a mixture of the 2 enantiomers. But in 1944 it was separated into 2 enantiomers, and they both have different optical rotation and things like that. And maybe they got the X-ray crystal structure of it. But yeah, that's kind of an interesting molecule. You can Wikipedia search this one. There's a little bit of stuff on Wikipedia about this, or Google. So nitrogen can participate in hydrogen bonding. So something like propylamine, it can the nitrogen can be a hydrogen bond donor, and the H can be a nitrogen is a hydrogen bond acceptor, and the H is a hydrogen bond donor. So there is some kind of hydrogen bonding, and that kind of affects the physical properties a little bit. But it's not as profound as alcohols. So if we think about methane, the boiling point's negative 161. Methylamine is like negative 6.3, so it's pretty much a gas at room temp, versus methanol, which is 65 degrees. So alcohols just have more of a profound hydrogen bonding interaction, I guess, with other alcohols. And then here's ethane versus ethylamine versus ethanol. It's the same kind of thing. And then how about diethylamine versus triethylamine? We see an increase in boiling point, and that's due to van der Waals interactions, because you have more of these ethyl groups around. Okay. Okay, and then spectroscopy. We emphasize NMR pretty much all through organic too. Reminder on how to calculate degrees of unsaturation, and you haven't seen too many examples with nitrogen, so now's our chance to review how to do nitrogen with degrees of unsaturation. Remember, with oxygen you ignore it, halogens you add an H, and nitrogen you subtract an H. That's kind of the general rule. Okay, and here's some fun practice for you. You can remember, what does UN indicate? Rings and double bonds, right? So benzene is 4 because there's a 1 ring and 3 double bonds. Here's some molecules: fluoxetine, which is Prozac, pseudoephedrine, and methadone, which is the opioid antagonist. Actually, no, it's a mild opioid agonist, but it's used in like heroin withdrawal therapy and stuff. So there's an interesting story of methadone, but it's actually used to kind of treat opioid addiction. But anyway, see if you can calculate UN for these. If you can't, you got to fix that. And office hours is a great time to fix it. So try using the formula, and given the rules up here, the answers are 8, 4, and 9. If you can't get those, you are not doing this right, and it will totally mess you up when you're trying to do NMR problems. Okay? It's pretty easy, but you got to do it the right way. So see if you can get 8, 4, and 9. And you can also look at the chemical structures of those and to see how 8, 4, and 9 map to the structures of those molecules. Okay, so here's a easy molecule, diethyl methylamine. There's N-methyl diethylamine. N-methyl diethylamine. And the NMR of this is essentially going to be, you got a pair of ethyl groups and one methyl group, right? And so one thing about nitrogen is it doesn't drag down the connecting atoms maybe as far as like oxygen, because oxygen, when you have oxygen like alcohols and ethers and stuff, it's usually in the 3 and 4 range. With amines, it's around the 2 to 3 range usually. Okay, but anyway, you can see how the NMR spectrum kind of maps to this structure over here. All right, the carbon NMR, pretty straightforward. Also, you got 2 downfield signals due to the there's the ethyl group and there's the ethyl groups and the methyl group, right? And like I said, yeah, the nitrogens are not dragged as far down as like with oxygen, OCH2s and OCH3s, which are kind of in that sort of 3 to 4 region usually. Okay, then we have what is this? Isoamylamine, I guess, or all right, so here's the NMR of it. It's pretty straightforward. You have a downfield NCH2, one other CH2, and then you have a CH, which is right there in the middle, connected to the methyl group, and then you have the pair of CH3s, and those are a doublet. Why are they a doublet? Because there's one neighboring CH. And why is this one a downfield one? Why is that a triplet? Remember to point out when you think about amines that the neighbors, you count the neighbors, but it's not including the nitrogen neighbors, because there are 2 protons on nitrogen. When we say it's a triplet, the triplet refers only to the CH2. It's not, we're not counting anything on the nitrogen for the N+1 rule. Okay, and then the broad singlet, 2H. The broad singlet, what is that? Well, that's the NH2. And that would also disappear with D2O, right? We talked about disappearing with D2O for OHs and NHs, right? Okay. Oh yeah, and one more thing. You know, this is a primary amine, right? A primary amine. And how many H's are on the nitrogen for a primary? It's 2, right? It's NH2. When we look at the integration of the NH and C2, that gives us a hint. Oh, it's a primary amine, right? What if your integration of your broad singlet is 1? What kind of amine is it? It's a secondary amine, right? Okay. Okay, so we'll see that. And you can try these problems. See if you can get them. C5H13N. Start with the UN. Make sure you can calculate the UN. And then we see the broad singlet of 2H. Is that a primary, secondary, or tertiary amine? Probably going to be a primary amine, right? It's going to be NH2. And then where's the amine connected? Probably the downfield signal with a 3.3, right? It's a CH. See if you can calculate this. Hint about amines. What does the integration of the peak at 2.5 tell us? It tells us it's primary amine, right? And if it's 1, it's maybe a secondary amine. If it's an amine with no broad singlets at all, That's probably a tertiary amine, right? Those are sometimes a little challenging to figure out, but that's the way you'd see that. Here's problem 2, C6H15N, and now broad singlet of 2H, probably another primary amine. See if you can get the structure of this. And here's one where we have a broad singlet of 1H, Was it going to be a primary, secondary, or tertiary amine? Probably a secondary amine, because you have 2 R groups and 1 H, right? All right. Don't be concerned about the fact that it's at 3.8 is irrelevant. We know what it is. It's the NH, right? Who cares where it comes, right? The chemical shift of an NH is kind of meaningless. That is okay. So what you should focus on is the integration, right? And the fact that it's 1H, that's important. And then there's 2 signals that are probably connected to that NH. It's probably the 2.45 and the 2.5, right? So with that, you can figure out the structure. And then just use your splitting to make sure everything matches the splitting, right? If you need help with these, come to office hours. Based on the integration of BS, what kind of amine is this? We said a secondary amine, right? Okay, acidity and basicity. So we got to kind of talk about 2 different things. One is something like LDA, which is extremely basic, extremely basic. And kind of like why it's extremely basic. The other thing is like simple tertiary amine, like triethylamine here. And it's also base. And that is extremely basic, but we need to talk about that also. So it's kind of 2 independent topics. Okay, LDA, extremely basic. It's good at deprotonating carbonyls and ketones and esters. And this is moderately basic, and it usually just neutralizes, like if you have hydrogen chloride around or something. It's definitely not as strong as LDA. Okay, so amines are weak acids, and that's why LDA is such a good base, right? Okay, so the way we kind of talk about the weak acidity of amine is we talk about the pKa, and we look at the dissociation, right? It's very disfavorable to go to the right here, and the K value is 10 to the negative 35, so it's 1, and then it's actually like 0.35 zeros, right? 1, and then it's very favored on the left, and that means that the right side molecule is very unhappy, right? And the pK is 35. And that's suggests how unhappy, how unacidic this proton is. It's not a very acidic proton at all. So how do we make LDA, which is essentially this top thing? You just use butyl lithium and rip off the proton very easily. And then that makes butane, which is the pKa of 50. Very easy to go towards the larger pKa value, right? So this is a very favorable reaction to make LDA. And then you have a super strong base for like ketones and deprotonating ketones and things like that. As a neutral species, amines are relatively basic, okay? So if we think about an amine and like hydrogen chloride or something, these will be pretty readily able to pull off that proton from HCl, and then the pKa is about 9 or 10 for an amine, just like a normal amine. Okay, think about an alcohol. Do alcohols do this? You always go towards the larger pKa value, right? And so alcohols can do this also, but not as favorably because the pKa is larger than -8, but not as much so as like an amine, which is 9 or 10. So an amine is kind of used as a base, like to absorb HCl. Okay, nitrogen's more basic, oxygen's less basic. Amines are more basic than alcohols because nitrogen is slightly more electropositive and can stabilize a positive charge. So in this top example, the nitrogen's positive and it can stabilize the charge better. Okay, and here's another example. And you always go towards the larger pKa value. Got an amine, we got a carboxylic acid. We go towards the larger pKa, and so is this a favorable equilibrium? And the answer is yes, it totally is. The amine can totally rip off that proton from carboxylic acid. What about diisopropylamine and a ketone? Is that a favorable equilibrium to make the enolate, to make the ketone enolate? No, it's not, because you don't have strong enough of a base. Amine is not strong enough of a base to rip off a ketone proton. Indeed, this might actually form the enamine, because remember that secondary amines react with ketones. This is a little sterically hindered, so I don't know if it would actually form an enamine. But anyway, yeah, not a favorable equilibrium. What about LDA? We've talked about LDA 1,000 times as a super strong base. So now with the equilibrium, ketones 20 and the amines 35, is this favorable or not? Totally favorable. Yes, it'll rip off that proton. And that's why we always emphasize LDA as a good base for deprotonating ketones and things, right? Okay, and then the other thing is anilines are not as basic as alkyl amines. Anilines are not as basic as alkyl amines. So the pKa is 4.6. And what was the pKa for a normal amine? You don't think about pKa of the amine. You always think about pKa of the conjugate acid, right? Because that's how you think about basicity. So if this was a normal amine, what did we say the number was? It was like 9 or so, right? 9 or something. So those are more basic. This is less basic. An aniline is less basic. Why might an aniline be less basic and less prone to go grab a proton? And that is due to the fact that the aniline actually has a benzene, and we can resonate the electrons around. So the nitrogen kicks down, and the double bond breaks, and you got a negative charge, and it's going around and around the ring. And so this is kind of a resonance stabilized system, and when it's stabilized, it's less reactive. Less reactive is going to make it less basic, and so that's why an aniline is going to be less basic than like a normal amine. The nitrogen lone pair. That's the other thing about the product is also less stabilized because it doesn't have that opportunity with the lone pair to do the same thing because the lone pair is gone now, right? So the left side is more stable by resonance, and the right side is less stable due to lack of resonance, right? That makes sense? So there's more resonance stabilization on the left, and there's less resonance stabilization on the right. And overall, that just makes this equilibrium not as happy, and that explains the kind of decreased basicity of an aniline. Okay. I think. All right. So we finished the conceptual stuff from amines, and we usually do that through PowerPoint. We don't have too much time to get into the reactions, but there's a little bit, and it's some pretty easy stuff. So we'll get started in the reactions now. Okay, so number 6 is going to be synthesis of amines, synthesis of primary amines. Synthesis of primary amines by alkylation of alkyl halides. I'll explain what that means in a second. All right, it's basically an SN2 reaction. It seems like a very simple reaction. It's using your old organic 1 knowledge, doing SN2. So it's not that crazy. An example of that would be, say we have a alkyl halide, alkyl bromide, and you're like, I want to make an amine, a primary amine, right? That seems really easy, right? You just got a good leaving group, you just got to throw in the right nucleophile. Maybe you could use like nitrogen, maybe NH3, like, because we know that's a good nucleophile. NH3, and it eventually would turn into NH2. Seems like a great way to do this, right? It seems so easy. but there's going to be a little bit of complication, and the question is going to be what nucleophile to use, I guess. All right, so that's going to be what the issue is. So I'm going to show a bad method, then I'm going to show a good method. There's like two good methods. So first the bad method. The bad method seems totally logical also, so it's like, so the most logical method to be, oh yeah, just use NH3 to do this, all right? That seems like a logical method, but it's a bad method. We're going to call this direct alkylation too. Direct alkylation. So let's show the bad method, and we'll probably get into the good methods next lecture. Maybe a little bit this lecture. Alright, so the bad method. Let's take a bromide and just hit it with NH3, ammonia. NH3, right? So that actually will make the product. The problem is, and the mechanism is actually really easy too. The problem is that it makes it, but then it keeps going. So it makes it, but then your end product is not that. Your end product will be nitrogen with 4 propyl. It like keeps going and going. So you end up with this quaternary ammonium salt, Br- thing. Alright, so I want to make that, but it keeps going to make this. How does that all happen, right? And why is it a bad method? Because it doesn't make what you want, right? All we want to do is this, but it makes this. Okay, so what's the mechanism? It's really easy. What's the mechanism? Organic 1, right? SN2 reaction. Good nucleophile, good leaving group. Seems like we're off to a good start. What's the charge on nitrogen now? It's positive. We gotta take off a proton. Actually, I'm gonna go downward, I think. Okay, how do we remove a proton? With a base. Do we have any bases around? Well, ammonia is actually a good nucleophile and a good base, for a moderate base. Good enough for this purpose. So ammonia just rips off one of the protons. Takes electrons onto nitrogen. Alright, we're cool. We made what we want. The problem is that it keeps going. It sees more of the alkyl bromide. Now you have maybe what's even a better nucleophile than what you started. So this is going to want to react even more. So it's going to keep going. So you have a primary amine, and now you're making a secondary amine. Okay, I'm going to just skip that -H plus step, which assumes, loss of a proton. So it attacks, of course we'll have an extra proton, and we remove the proton, and we get a secondary amine. And then it does it again. Again, -H plus. And then you have a tertiary amine. Then it does it again, but you don't have the loss of a proton because there's no more protons to be lost. And you go from your tertiary amine, remember tertiary amine, secondary amine, primary amine. What's this one called? It's the quaternary ammonium. Ammonium. Why is it ammonium? Because it's got 4 things and it's got a positive charge. Yum. Alright, okay. So we wanted to do this, but we got this, and that's why it's a bad method. Alright. So we could say that it's bad because it keeps going and going. Reaction doesn't stop. The reaction doesn't stop, right? And you get left with a mixture of primary, secondary, tertiary, and quaternary amine. So you have a mixture. I mean, it's not like you only get this. You have some of this, some of that. Some, you know, it's just a big crazy mixture, and that's usually not what we want for chemistry. And indeed, the reason it kind of keeps going, and it goes even more aggressively, is each R group that you add, like 1 propyl group, 2, and 3, it actually enhances the nucleophilicity a bit. There's a little bit of an inductive effect, like electron donating group effect on nitrogen, so it's like even more aggressive each step to keep going to the end, undesired product. I should also say, sometimes your goal is actually to make the quaternary ammonium, and if your goal is to make the quaternary ammonium, well then that's actually a good way to do it. Just blast it, you know, an alkyl halide with NH3, and then just let it go all the way, and then you'll make a quaternary ammonium. Because sometimes these actually have interesting properties, and it's like what you want to make. But in this case, we want to make the primary amine. Okay, so I'm just going to show one of the improved methods real quick that avoids this whole problem. We'll talk about mechanism and stuff next time. But this is improved method number 1. We have improved method number 1 and improved method number 2. We'll do number 2 next time. So number 1 is going to be using azide. And azide just means nitrogen, 3 nitrogens, right? Nitrogen, double bond nitrogen, double bond nitrogen is called azide. And this avoids the over-alkylation problem. Avoids over-alkylation problem. Okay, so I'll just show it, and we'll talk about the mechanism next time. It's pretty straightforward. So here I'm going to just do an example. Bromobutane, 1 bromobutane. So we're going to do an SN2, but we're not going to use NH3, we're going to use NaN3, which is called sodium azide. Sodium azide. Okay? Of course that's Na plus N double bond N double bond N. And it's, we have dot 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 dot, negative, positive, negative. That's azide. Negative, positive, negative. Alright, and it's just an SN2, so what's a good SN2 solvent? Maybe DMF. Review DMF if you want, that's in the SN2 chapter, I think chapter 7 or 6 or whatever. But yeah, it's just azide attacks, technically attacks on the other side, but it doesn't really matter. It's just an SN2 reaction, good nucleophile, good leaving group. Now you got an alkyl azide, nothing too crazy. Now we have a plus charge here and a dot 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 negative charge there and a neutral charge there, so it's a net neutral molecule. And this is what we'll talk about next time. It's just, all you got to do now is convert the azide to an amine. That's actually pretty easy. You just use lithium aluminum hydride or trusty reducing agent, a little bit of H3O plus workup, and then you got it. So it solves all the problem of the over-alkylation and the primary and secondary and tertiary and quaternary amines. All you do is an SN2 with sodium azide and then reduce the azide with lithium aluminum hydride. Okay, so I'll show a mechanism for how this works. It's really easy. Just H- attacks, I think, the middle. The H- attacks the left nitrogen, and then you do a little bit of electron pushing, and then it falls off. Everything falls off. Make N2. N2 is the byproduct. Cool. All right, that's it.